Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Barry Madore and Wendy Freedman with us today. Hello, Barry. Hello, Wendy.
Hello. Good to see you.
Yeah, well, thank you so much for agreeing to talk about your very awesome article. It's very cool. And Wendy, where are you located at?
I am currently in Chicago, Illinois, in the heat.
Well, it is July 28th of 2023 as I record this, and I'm in Phoenix. And probably
got more heat.
We got more heat, but not as much humidity as you get in Chicago there. So very cool. And Barry, where are you located at?
I'm over on the San Andreas Fault.
Hopefully not active today.
No, they're not active. Here in Pasadena, temperatures rising.
Yeah,
air conditioning.
Yeah, I see that we have a third party there laying on the floor. So
There'll be more.
Completely whacked out.
He looks very relaxed.
One of five.
One of five. Whoa, very cool. Very cool. Are they all that size, or do you have little ones?
Oh, they're smaller. They're huskies.
Very cool. Very cool. Well, they must be enjoying the somewhat cooler weather in Pasadena there. So
they stay in the house.
Yeah, cool. Let's see. And Wendy, what do you like to do for research?
Ooh, I like to do the extragalactic distance scale and measurements of the Hubble constant, and trying to improve those measurements so that we can get good constraints on cosmology. And I really like methods for measuring distance that are based in astrophysics, in particular stars, where we can learn something about their characteristics so that we can get at the systematics that might be impeding the accuracy that we eventually like to achieve.
Cool. I like stars. Very good. And Barry, what do you like to do for research?
Well, I'm sort of a details guy at the same time as a broad brush person. My first 40 hours of the week are spent on Cepheids, tip of the red giant branch, distances.
Cool.
And the other 40 hours a week, I am a practicing philosopher of astrophysics.
Awesome.
So I attempt to bring some philosophically oriented aspects to the papers to broaden the perspective. And I hopefully try to use that in my day-to-day astrophysics itself.
Absolutely. Very cool. And we will see it as we get to it. But yeah, this one has some awesome aspects that Barry just mentioned in this article. So check it out. And that is going to bring us to this very awesome AJ article. Excuse me. It's open access, people. It's the open access era. You can go grab a copy for free. Go get one. Quantifying uncertainties on the tip of the red giant branch method. And Barry and Wendy, take us away.
Okay, I would like to put the tip of the red giant branch into, first of all, the historical context and lead the way to why we undertook to do this paper when we did, and why it may seem a little bit complicated, why it's absolutely necessary now that we are moving towards much more demanding determinations of distances to galaxies.
Cool.
Should point out that cosmology has always been in a state of crisis, right from the very beginning. It's nothing new.
Indeed.
But what is sorry, go ahead.
Indeed, yes.
Well, what is new, I think, is that most people don't realize that the tip of the red giant branch has always been part of that crisis, either precipitating it or ameliorating those crises. And it's now more than a century ago that Harlow Shapley invented the tip of the red giant branch method. He was working with photographic plates, and he was working in the blue, which is what technology provided him with. But he was trying to set up a distance scale within our galaxy in order to find a cosmology, to find the size of the then known universe.
Yes.
And one of his probes were galactic globular clusters. And in order to get a distance to them, he came up with the bright idea of using the brightest 25 stars in those globular clusters as standard candles. Well, as it turns out, they're not really standard candles at all wavelengths, and it's very difficult to do. And he basically built his island universe cosmology around it.
Yep.
And got the wrong answer. But he was the one who started this all going, and it has ebbed and flowed through the last 100 years as being a distance indicator. And it's sat fallow for a while. And since Walter Baade is a distant relative of ours from the Carnegie Observatories, I'll pass it to.
Okay. Institutional.
Yes.
Yes, no bloodline.
I was gonna say, huh? I didn't know this.
So yeah, I think most people are familiar with the fact that Walter Baade changed the distance scale by a factor of 2, and but perhaps the details of the fact that he actually detected the brightest red giants in galaxies. He was able to resolve those because for the first time he could use red sensitive plates, and he was observing during the war when the lights in Los Angeles had been turned off.
Mhm.
And, he originally had set out to try and find the R Lyraes, and those turned out to be too faint. He discovered a background sheet, what has come to be known as Bade's sheet, and those were the first red giants to be resolved in nearby galaxies. That, of course, led to the discovery of 2 different kinds of populations, but also where the red giant branch stars came in. And then again, they didn't really surface in studies of the distance scale for several decades until CCDs became widely available on telescopes, and beginning with work by Jeremy Mould and Mike Rich and others began to look at some of the dwarf galaxies in the Andromeda group, some of the Andromeda companions. And then when the CCDs became available on the CFHT, which was where Barry and I were observing, we also began studying nearby resolved galaxies with CCDs, both for studies of their Cepheids, but also for the tip of the red giant branch. And that's when it became apparent, when finally the I band and CCDs and their red sensitivity allowed the measurement of the tip of the red giant branch in globular clusters.
Cool.
And that was kicked off with a paper that was published by DaCosta and Armendroff, in which they studied globular clusters in the Milky Way galaxy that had a range of metallicities. And what they were able to show was that the tip of the red giant branch in the I band had a roughly constant luminosity independent of the metallicity. And they were able to compare with theory, and theory also confirmed that in the I band, the bolometric correction was just such that you would expect a constant luminosity in the I band.
Nice.
So that really kicked off. Sorry, were you going to add something?
Nope, very nice, good.
It kicked off for us the ability then to study a number of galaxies nearby where they had different metallicities, different star formation histories. And we were able to show again that they had giant branches that could be resolved, that you could measure their tip in the I band, which was constant with color or luminosity. And when we did that in Lee, Freedman, and Madore in 1993, we were able to show that those distances agreed really well with published data in the literature for Cepheid distances, R Lyrae distances, and so on, at a level of about 10%. And that's the level of accuracy that we were achieving as we went into, and that was the goal of the Hubble Key project, was to try and measure distances to galaxies using Cepheids at a 10% level. But what probably is not as well known is that we did use the tip of the red giant branch distances as a check of the local distance scale. That was one of the reasons that we could have confidence in our statement that we had measured the Hubble constant to 10%, because of the good agreement with the tip of the red giant branch and Cepheid distances at that level.
Yeah. I might point out also that there was a change that occurred in the Lee, Freedman, and Madore paper And that was, prior to that, people were just basically putting their finger up on the diagram and saying, well, that looks like where the luminosity function truncates, and drawing a line. And that was good enough. I mean, when you're playing around with something that no one else has seen before, you don't necessarily build up all the infrastructure to optimize it. And in fact, there was a little bit of a controversy because Alan Sandage had just published a Cepheid distance to M33.
Okay.
And Christian and Mold had a tip of the red giant branch distance to M33 at the same time, and they didn't agree. Well, what a surprise, huh?
There's our crisis again.
Right.
Well, that, points out again when CCDs came online, how things really radically changed. And Barry and I published a paper on M33 for the Cepheids also that showed that when you could correct for reddening, which CCDs allowed you to do because of the multi-wavelength, the fact that you could measure those with a CCD in one shot, correct for reddening, you could deal with crowding of stars that would contaminate the light from the Cepheids, you could begin to ask questions about metallicity and so on. Those began to converge, the Cepheid distances and the tip of the red giant branch distances. But as Barry points out, that difference actually was a factor of 2. That was the whole factor of 2 debate in one galaxy, was the difference between the tip of the red giant branch distance and Sandage's Cepheid distance.
And I'm quite convinced that both Christian and Mold felt that the tip of the red giant branch was at fault. Okay. Because it was new and because people hadn't thought about it much. But it was technology, as Wendy said, that always seems to precipitate certainly better data, often at different wavelengths and in ways that challenge the things that we thought
existing data.
Existing data, which, I mean, with Shapley, he was working with photographic plates in the blue, and that was not optimal. And moving to the infrared makes it much more, I mean, the I band makes it much more optimal, and you see things that you didn't see before. And so we introduced, well, through the military and through what people would call AI these days, digital technology for detecting edges. And these edges of the luminosity function are really just the marginalized over color luminosity function. And it shows a sharp discontinuity. You have the tip of the red giant branch being the discontinuity, but it's generated by stars coming in on the giant branch and then disappearing over onto the horizontal branch.
Yes.
And
helium ignition.
The military was always interested in looking down to find tanks and military transports on the ground. Yes. They are very unlike a lot of natural things. They have sharp edges. The same thing looking up. If you're looking for a plane in the sky, they have sharp edges on their wings. And so they were more than interested in using digital technology to find edges. And that's where the Sobel filter comes in.
Okay.
Digital data, whether it's an image or whether it's a luminosity function, you run this filter over your data and you come up with a response, which is the Sobel filter edge detector response.
And that allowed you, so provided a way of measuring the tip in a quantitative way and determining the uncertainty. So it really, and it's reproducible, which had not been possible before.
We thought it was reproducible until other people started introducing other ways of doing it, which didn't reproduce. But that was one of the other motivations for this paper, was to show an optimal set of Sobel-like filters, and the whole idea of when do you smooth the data and when do you not? What are the consequences of using these filters? Do they introduce bias and give you the wrong answer, or do they just introduce noise in which you can quantify that? But through the simulations, those were the sorts of things that we were looking to quantify. And We did it early on, 30 years ago, and Wendy can tell you about that.
But we're interested in addressing, how well could we measure the tip? And at that time, we were concerned about how many stars you needed to define the tip well.
Right.
And so we were particularly concerned that if you didn't have enough stars to actually measure the tip, then you would underestimate it. You wouldn't have enough stars filling the bright end of the luminosity function. And so that you would measure a tip that would be too faint.
Mhm.
And that was really our motivation early on. And so we did a number of simulations to try and understand how many stars would allow us to measure the tip with some reliability. And as Barry mentioned earlier, a motivation for this one now is as we're trying to get higher and higher accuracy, 10%, which was what we were trying to achieve 30 years ago, isn't sufficient anymore. And there are a lot more issues that we have to address, particularly as we're trying to use the tip of the red giant branch to greater and greater distances. And so we have to worry not only about sample size, but issues of, how does smoothing, choices about smoothing, choices of the Sobel filter,
Right.
and the issue of crowding by other red giant branch stars as you go farther in distance and you have more stars that might be overlapping. But also, one thing we should make clear is that this method is best used in the outer halos of galaxies. It's one of its advantages is that unlike Cepheid variable stars, Cepheids are young stars. They're only found in the disk where there are regions of star formation. They haven't had time yet to diffuse away from the regions where they were originally formed. So they're near regions of dust, regions where there's ongoing star formation, high surface brightness, more crowding, contamination by other stars, particularly other red stars. And we'll
Mhm.
get back to that in a moment.
Indeed.
But so you don't have any choice with the Cepheids. When we're measuring a Cepheid distance, we're in the disk and we have to devise means of correcting for reddening, correcting for contamination, correcting for metallicity effects, which are much larger. Whereas the tip of the red giant branch, there is an old population in the halo of galaxies, and one of the things that Bada was able to show also, but so we can avoid a lot of the contamination. There's no dust to speak of in the halos, and there are a lot of advantages with respect to the kinds of systematics that could affect your distances.
Cool.
And so one of the other motivations for this paper was trying to understand what happens when you allow for more and more crowding, which of course is going to be a systematic effect.
Yep. Nice.
So one of the sub pieces of advice, Wendy's already said it, go out into the halo. But some people have said, well, I only have this image of the disk or a partial way out of the disk, and I'm going to attempt it. And that's a doomed effort. And it's caused a lot of consternation because they don't get the same answer. Of course, if you're in the disk, you've got the dust, it's going to affect the tip of the red giant branch stars that are on the other side of the disk.
Sure.
And they'll give different answers. So you shouldn't expect to get the same answer as in the halo. And you should expect it to be fainter and expect the distances to be larger. So why people insist on doing that, I don't know. But they also try to change the filtering process to try to accommodate all of the other stellar populations that are in the color magnitude diagram at the same time.
Yeah, okay. Mhm.
So they make their lives miserable by just not by attempting to do something which is really much more complicated and probably systematically wrong in any case. So stay out of the disk. Don't attempt to do a full population synthesis modeling of the color magnitude diagram when all you want is something which is the pure population 2 contribution to as a distance indicator.
Yes.
It can be done and it should be done. And we're presenting here methods to do that in the most efficient way. So the paper is structured both as a prescription for when you are setting up your observing program, what to do and what not to do, How deep should you make your exposures? How many stars where and out in the halo, and how much of the halo should you be covering in order to get sufficient numbers of stars to fill the luminosity function, to define the tip properly, both in terms of numbers and in signal to noise for those stars, and then have a quantitative way of both understanding what's happening with crowding.
Yes.
And if you go out in the halo, you can just look and see what the crowding is. And the only stars out there are the brightest stars at the tip of the red giant branch plus a smattering of AGB stars. And you can see them. You can see whether they're crowding one another.
Right.
So,
Cool.
so that was the reason for having these simulations, holding each of those parameters constant and moving one of the others, and seeing how the response to the tip of the red giant branch, how it degrades, and whether it biases itself with degradation, or whether it just falls apart. And I think it's important to know, and people can see it, and then they can judge how best to analyze their data, or how best to structure their observing program.
Nice.
I'll go to the first figure. Oh, you're already at it. Okay.
Now let's see what that luminosity function looks like. Here we go.
Yeah. So you want me to go, Barry?
Yeah, sure. Yeah. This is a cartoon.
Yeah, this is just a schematic of what the luminosity function might look like in the halo of a galaxy. So you have a small number of asymptotic AGB stars that are brighter than the tip. And then you have a red giant branch luminosity function, a steeper luminosity function that there are more stars, more red giant branch stars than asymptotic giant branch stars. And so as you're coming down the luminosity function, sort of down in this plot, but as you go to brighter magnitudes, you eventually run out of stars on the red giant branch, and you see this very steep decrease. And then you see the asymptotic giant branch luminosity function kicking in. But what we're trying to measure is the position at which this discontinuity appears. Now, we haven't said anything about theoretically why the red giant branch method is such a good one, but maybe just briefly say that these are stars that low mass stars, they have helium cores, and the cores are degenerate. They have a shell of hydrogen about the helium core, which is then burning and putting more helium onto this degenerate core until it reaches a certain mass. It occurs at a temperature of about 100 million degrees. And at that point, you can ignite the triple alpha process of helium burning. Because the star is degenerate, the core, it can't expand to cool off. And so a thermonuclear runaway ensues, and you get this very rapid burning of helium, and effectively you lift the degeneracy. This happens very, very rapidly. The star then settles down onto the red giant branch, and
Horizontal branch.
Horizontal branch.
Sorry, settles down to the horizontal branch and disappears from the red giant branch luminosity function. So this discontinuity that you see here is when these red giant branch stars in the course of their evolution disappear from the color magnitude diagram, and we see that discontinuity. So it's the point at which the core helium flash occurs.
Yes.
Theoretically very well understood, has been modeled for decades, and very well understood physics. It's nuclear physics. It doesn't depend on the mass of the original mass of the star. It only depends on the core mass, and this occurs at a essentially constant core mass, constant luminosity. And so, sorry.
And I'll give a shout out to Aldo Serenelli's paper in 2017. That was a really nice one if you're really interested in the nitty gritty stellar physics of that. Very nice.
Yeah, and there's been some beautiful work done on this, and it, I think, is one of the reasons why we are excited about the tip of the red giant branch, because the physics is well understood, and we know why there should be this discontinuity. It's amenable to empirical calibration, and of course, there will be systematics in any method, but this one in particular has the opportunity to really nail down what the systematics might be and quantify what the systematics are. And so it makes it a highly desirable method for measuring distances.
So some soundbite words to take away. The tip of the red giant branch is a standard candle, especially in the I band. But all of the other standard candles are really standardizable candles because they have many other parameters that you have to understand and calibrate before you get to your final distance determination. The tip of the red giant branch, bolometrically,
Yeah.
it's there. The other throw out is first principles physics. You can derive this from laboratory astrophysics. It's not like you have to understand, convection, which we don't understand. It's not like we have
magnetic fields, rotation,
magnetic fields,
blah, blah.
or for that matter, variability and instabilities of a surface. Okay, it is about as close to ideal as you can get, other than the fact that it's a little bit fainter than the brightest Cepheids. It's brighter than the faintest Cepheids, but that's something that we'll talk about a little bit later. But it is.
And just to add to that, I mean, because they're not variable, you don't have to measure 12 epochs, say, to get their light curves. So although they're fainter, in terms of overall observing time, it's not that much different because you either add up 12 epochs and to get a deeper color magnitude diagram for the tip of the red giant branch, or you spread them out in time so that you can measure the variability for Cepheid. So in practice, it's not really much of a disadvantage.
Right. And just to tie a loop around some of the previous conversations, in the bottom here is the Sobel response. And so its primary thing here is to pick up that edge, right? That drop off between the RGB and the AGB.
Right. It is just a derivative. It's measuring the amount of numbers in leading edge and the numbers on the other edge, taking the difference and giving you the first derivative. So it's nothing special except that it has a name and that it's widely used in the image processing community. So it's well known, it's been well tested, and its properties are understood. It's not mysterious by any means. But one other thing that I was going to mention, yes, by going out into the halo, not only do you get to just a pure population 2, but you get away from all of the dust in the disk. And we don't believe that there's an enormous amount of dust in the halos of galaxies. We do have a foreground component, which everybody can correct for and do. But at the same time, the tip of the red giant branch is measured in the I band, which is, it's not far infrared, it's not mid-infrared, it's closer to the infrared, so it's less affected by extinction automatically. There's less dust and the effects are smaller. So there's some other advantages to the tip of the red giant branch over, say Cepheids, where you have to deal with all of those things in order to turn it into a calibratable distance indicator.
Cool.
So we turn to the simulations.
Sure, let's go. We're going to do a few preliminaries. Precisions. So let's talk about the simulations. So what are we doing in those simulations?
Well, we're looking for the effects of 3 parameters on both the precision, that's a statistical measure of the quality of the distance, which usually depends on the numbers of objects that are entering into the measurement and the the quality of the data that goes in to the measurement. And we're looking for accuracy and how it responds to these parameters, and accuracy being whether you've got the right answer, not just a good or bad answer, but the right answer. We're looking for bias in
Yes.
whatever we're doing, and the simulations allow us to search the parameter space, control the parameter space, and do it as a laboratory experiment would be, where you control your parameters and look for the effects of it. So we run through a range of photometric errors. We run through a range of total numbers of RGB stars. And we also show what the effects of smoothing the data are in order to compensate for something, just to show. So here we go. I mean, Wendy, do you want to describe the first one at least?
Let's do a global and
the upper left panel.
Okay.
This is sort of the target.
Okay.
Yeah, so I can't read it. So if you blow it up, and then I just remember how many stars we used. And
Yep.
Okay, so this is taking a population, so a large population of stars, in this case, red giant branch, you have 120,000 stars that are contributing to the luminosity function, and a smaller population of AGB stars, which is roughly consistent with what we see in the halos of galaxies. And so starting off with 0 errors in the tip and a very small smoothing parameter, only 100th of a magnitude.
Okay.
And so you can see that, so if there's the luminosity function in the top panel, very sharp discontinuity. And if you go to the bottom, then you take the first derivative. And so you can see where the very sharp peak comes. There's no ambiguity. Here is the tip that we're measuring, and there's no noise. So of course it's very simple to do. So then as we walk through, maybe to the right, now we're adding a 0.02 magnitude error into the luminosity function. So you can see there's slightly more scatter in the luminosity function. And as we walk through, the width of the Sobel filter is going to increase. So if you walk through, so the 0.05 magnitude errors, 0.10, and you can see now there's a lot more noise. There are other peaks that are coming in, but the position of the peak is very well determined. That is both in precision, and precision is lowering, but the accuracy remains very high. There's no ambiguity in the position of where the Sobel filter is telling you that the discontinuity lies. So all the way down, there's on the bottom right there, the error is now up to 0.2 of a magnitude. Again, a lot more noise. You can see a lot more noise. The discontinuity, it says luminosity function is being smoothed over because of the uncertainties, photometric uncertainties. But again, you can measure, the first derivative here of the luminosity function. You can see where it's changing.
But it's worth pointing out that you would be pretty hard pressed to do better by just doing it by eye. I mean, that's a pretty
okay.
You look at the luminosity function here. It doesn't look like there's much to be found in terms of something distinctively edge-like, but the Sobel filter sees it, it finds it, it brings it back out. And one of the things that's subtly in these plots now is that there's some lightly shaded lines, and we came up with a technique that allows you to suppress the noise in the Sobel filter by weighting the output by the expected random noise in the data. Okay. So it will trigger to noise spikes, ups and downs. It's finding ups and downs, and when you have more and more noise is characterized by spiky reactions to it. Well, but from statistics what the random errors on those individual data points are, and the ones that have larger random errors would be suspected as being good examples of things that should have a spurious noise peak. And so unfiltered is the light line, and then the filtered value shows you the filtered output. And you see also that the underlying response of the Sobel filter itself gets narrower and better defined when it's been appropriately filtered. So this is something new.
Yes.
We've been using it for a while, but we've introduced it here to show you explicitly what its attributes are.
Cool. Very cool. Nice.
So they're just walking through the different plots. Many of them look the same, so we probably don't want to spend too much time looking at all of them, but just give you a general sense that you can vary not only the photometric errors, but you can vary the smoothing parameter that's applied to the luminosity function, and then start varying the amount of contamination or crowding, and then look at the impact on the Sobel filter as you are varying different parameters. So this next panel's you're increasing the photometric noise from 0 to 0.2 at fixed smoothing. Whoops. And if you want to go down to the next one.
Yep, absolutely. You're doing the driving. Okay.
Okay. And so now you are changing the numbers of stars here in the luminosity function. So there's 1,200 stars instead of 120,000 stars.
Right. See it? Yep. Yep.
And
Very
things
cool.
are getting a little bit dodgy.
Yeah, so you can see that statistics are much poorer. That you
Ooh,
really
yes.
want to ensure
Yes.
that you have enough stars to define the luminosity function well.
And so if you were down in the bottom right panel, you
Mhm.
might think that you've got the right answer sitting over that big spike that's brightward of the true answer.
Right.
But what these simulations are telling you is if you're down in this regime, you're in the danger zone, and you either bail out or give yourself a very large error bar, because the width of that response function is just telling you something about the noise properties of the data set. It's not telling you really anything about the tip at all, because you
Now, of course,
see
these
the
are
tip.
large errors right here. This is 0.2 of a magnitude. You're somewhere probably pretty close into the disk if you're going to have errors that large,
Or very far away.
or very far away. Yeah.
Or very far away. Fair enough. Okay.
Yep.
Yep. Very cool. Good. Glad you're looking at this stuff. Very good. Okay. And then 4. And then, okay, we are almost totally noise here. This has got 124.
Okay, so 124 stars. You can go home. Just put in another observer.
But if you go to the top
Okay.
of this plot,
Okay.
you're not going to be saved by really high quality data.
Right. Right. That's just, that's hilarious. Okay. Very good.
Going.
So these are understandable. They're intuitive, that things should fall apart at some point. What we're trying to do is say, these are the parts of parameter space where it does fall apart, and you shouldn't go there.
Very good. You have been warned, people.
Yeah.
Don't go there.
Rough trail ahead.
Okay. And then we're going to shift the plots a little bit here. So let's zoom out that one. And yeah, this is increasing photometric noise. Yes.
Got larger smoothing than before.
Yes. 0.05.
So this asks the question, if you go ahead and want to smooth, does it do something terrible to the response function's accuracy? Does it bias the result? And many people have argued, unsuccessfully in my opinion, that the presence of the AGB means that when you run the filter over it, will draw things away from the discontinuity. And what this series shows is that that's simply not true. And I think the epilogue, if we ever get to it, part of that is saying that what happens far away, or even slightly far away from the discontinuity, has no influence on the detection of the discontinuity. If you're walking up to this cliff, it
Yes.
doesn't matter whether there's a pile of boulders at the bottom of the cliff or just sand. It doesn't matter whether there's pigs and elephants sitting on the crest.
There go the epilogue.
Behind you. It's when, well, no, we don't want to read it right now, but we
Oh,
should.
but you're going into it.
Okay.
Going into
All
it.
right. So let me read it.
I think it's a great analogy. It's a
It
great.
is a great, it's a very visually, it says what's going on.
Yeah.
Okay. You will know when you find the edge, not by having information about what's behind you.
Mhm.
You will either fall off of it if you come from the top, or you will crash into it if you're coming from the bottom. But it doesn't matter whether you're climbing over boulders at the base.
Yeah.
That's just a pillar, and
Mhm.
it doesn't matter what's going on in the weeds and grass at the top of the hill. It's only at that very instant, which means that's the precision with which you will know whether you've fallen off the cliff or not.
Yes.
And the Sobel filter does that. It's looking one step ahead, one step behind, moves over. It's not looking.
Another way of coming at this, and we've done work along these lines too, and there's been a lot of effort to do a maximum likelihood measurement where
Yeah.
you can estimate what the slope of the red giant branch luminosity function would be, what the slope of the AGB luminosity function would be. But as Barry's saying, you don't care what when you're down in the slope, it knows nothing about the edge. It knows nothing about that cliff, right? Which in that first figure, you see it's a very sharp discontinuity. And so that slope is not the determining factor. It's when do you hit the edge? That's what we're measuring. And it's, using these techniques, Sobel filter and so on, you're measuring that first derivative at the point where the core helium flash is occurring, you're dropping off that cliff. And that's what's important. It's not what's happening out far away from
This way. Right.
That's the essence of discontinuities in mathematics. They are not predictable. You cannot predict where a function is going to become discontinuous because it's only continuity which allows you to make predictions.
Fair enough. Yes. Yes.
Okay. So
Yeah.
enough
so
said.
it's why the method works as well as it does. It's measuring that tip with precision and minimizing the systematics and choosing fields that get you outside of the sort of systematics we're all used to dealing with in dealing with the Cepheids.
Yes. Cool. Okay. So we jumped a little bit there on our epilogue, but
We were discontinuous, I think.
doing so great. Okay. Let's see. What would you like to cover
Want to
next?
do the crowding ones?
Yeah, let's do the crowding because that's an important consideration here. Let's see. There's our one table simulations. Let's see. Crowding. Still doing smoothing.
This is where we get to producing images.
Yeah.
Further down. More.
More. Yeah, we'll get there. It's all good. More smoothing. And intermediate.
Yeah, we're walking through parameter space, literally.
Yeah, no, it's a very thorough, complete analysis. Very nice. Let's see. Here we go on this. So
well, the thing about the takeaway for smoothing is, yes, the Sobel filter will get wider, but you have to not use the width of the Sobel filter. You either should use the simulations to guide you as to what the uncertainty on the tip value is, or you should divide by the square root of the number of stars that are being used inside the Sobel filter. And many people have not done that. And when you do it, the numbers converge, and
yeah, so otherwise you got a root.
It becomes stabilized because you're applying a square root of n correction to the width.
Yep, exactly. Yep. Okay, crowding. Let's go to crowding.
Well, this is still smoothing, and these are diagnostic plots that people can use.
Okay. Here we go. Here we go.
So this is a little bit different in as much as it goes and shows you what the simulated CCD image of a particular field would be in the presence of AGB stars. And you can see them highlighted as red dots there. And so this is, this is a lot of stars, not a huge amount of crowding. You can look at it and see that the AGB stars are more or less separated, and there might be a few that are crowding one another.
What are the black dots? Got black dots in there too.
There are black dots, and those are the red giant stars. Well, the black dot is something that actually got identified as being crowded.
Got it. Okay.
And you can see
another point maybe to make while we're back on the luminosity function is that, there have been concerns, and certainly we were concerned early on about how well you need to know the AGB luminosity function, and, do we have the right slope, et cetera, et cetera? What if it has a different slope? But what's really clear in walking through these simulations is that the AGB luminosity function, it's adding a pedestal. But the actual slope, there are fewer of them, first of all, so they're not having a big impact, and whether the slope is slightly different or not doesn't impact whether or not you can measure the discontinuity. Turns out not to be important.
Right. It's the one step behind me, doesn't matter.
It's the same issue. Yep.
Exactly.
And you can see it in the luminosity function. It's just a pedestal.
Yes. Base.
So this is the best case scenario, and then you start moving down in the simulations.
So this is more. Okay.
Right.
RGBs.
The answer is not much bias. There's a little bit of noise in the Sobel response.
Right. A little bit right there. Let's crank it up. And
okay, now you start to see this, what looks like an AGB population in the left-hand diagram. Those are in fact stars that have been self-crowded in the red giant population, and then they spill over and produce stars brighter than the tip.
Sure.
Okay.
That.
So they're producing an annoyance, but the fact is that the tip is still being detected, albeit a little bit biased, but you can see that the original tip where it is, and the response of the Sobel filter sees it. Now you have to go to pretty extreme crowding in order to obliterate the discontinuity, and we've done that, and you can see how it degrades by going further.
More. Let's go one more. Oh yeah, here we go.
All right.
Now we got
so now you've got a lot of stuff there, which people would ordinarily say, oh, well, that's a huge AGB population. But it's not. It's you can look at the star densities, and you can predict, and you can see from the simulations that is crowding, self-crowding of the stars at the red giant branch, but they're spilling out. They just deplete a little bit at the bright end, but they don't change the existence of the stars that are uncrowded, which are still being detected as the tip.
And just to remind people of, a factor of, if you crowd a star by a star of equal luminosity, that's a change of 0.75 magnitudes.
Which is the top of the plot.
Yes. Okay.
And it was chosen that way to be illustrative, that you'd have to have two stars of exactly the same magnitude pushing things up there, but it's more likely this is a luminosity function in and of itself, reflecting the luminosity function of the red giant branch. So that there's more stars that are fainter.
Stay in the halo.
Again, it's simply stating the obvious, which is you're better off in fields where you don't have a lot of self-crowding.
Stay in the halo. Stay in the halo.
Yeah, move out.
Mm.
Protect yourself against this. You can do it.
Yeah. Okay. And
And
finally-
there's the final one where it all just
Really?
blows up.
Oh boy. Oh, look at that. Yeah, we lost it there a little bit.
But yeah, but you can imagine somebody
2 million
picking
red
the
giant branch
brighter.
stars in this frame.
And calling it. Yeah. Hmm.
So
Beware.
beware. But you can self-test. You can see what the star densities are, and know what the crowding is going to be.
And
And
that's important. It's not as if this is creeping up in a way that you're unaware of. You can
Right.
see the effect. Yeah.
Good. Very good. Awesome. Okay. We had that awesome. And that was it for the main paper. And that covers the 3 uncertainties. We did cover the epilogue there. It's epic epilogue. Check it out, people. And then we have a couple of interesting appendices. You want to talk about the appendices a little bit?
Just quickly, because they may not be intuitively obvious what the Sobel filter is and what its parents and progeny are. But here in that mound, the binomial coefficients of Pascal's triangle. Okay, you can either drop balls down a little
Yes.
structure and see them bouncing and taking their stochastic paths of either going to the right or the left.
Yes.
And that's what Pascal's triangle is. But if you work your way down, I mean, Pascal's triangle, if you take it to an extreme, and the binomial theorem proves this, that it converges on a Gaussian.
Yes.
Okay, so there's a very nice digital hierarchy here of going from just points and coefficients to something that's more continuous and more familiar and has properties that we all know and love.
Yes.
Now, one of the filters that can be used is the derivative of a Gaussian. It's called a DOG, a dog.
Mhm.
And the derivative of a Gaussian is an edge detector. Okay, because it goes up on one side, crosses through 0, and goes down the other side. So, so down at the bottom here, if you took the derivative of Pascal's triangle in the way that you would do the derivative of a Gaussian, you go to the next plot just below, or pile of the pile of the data. I don't know what to call it. It's just a pile of numbers. But
Figure 23.
yes, so the first derivative of the binomial coefficients are now put into this diagram, and the first one is 1 minus 1, and the second one is 1, 0, minus 1. That is the Sobel filter for a digital edge detector.
Good.
And every one of the things below it are, if you like, smoothed or broader versions of edge detectors. And you can choose them to your heart's delight and find out which one you want to go to. If you want to smooth over many, many pixels, you can pick one deeper down.
Go down.
Okay.
Cool.
This is a way of naturally smoothing without saying, okay, I'm going to use a Sobel filter here, and then I'm going to smooth it with a Gaussian over here with a different thing. No, this is the way you would optimally do it, where you get the smoothing and the larger sampling of the luminosity function to get something which is consistent. I mean, it's exactly identical to the Sobel filter, but it is converging slowly onto the Gaussian, the difference of Gaussian.
Yeah. Cool.
So
Very nice.
that's.
And honestly, I had never seen the first derivative of a Pascal triangle, so I found this part fascinating. It was great. And there's a lot more great stuff here in the appendices as well. I invite you to check it out. It's very complete, very nicely done. Very nicely done.
Okay.
Okay. Give me a takeaway message. what's the takeaway? What do you want to say on the takeaway?
Takeaway is that the tip of the red giant branch is a method that's like all methods undergoing an evolution in terms of greater accuracy in its application. And the takeaway message is, if you want to have the most both precise and accurate measurements that you can get using the tip of the red giant branch, move out into the halos of galaxies where the dust effects are small, where crowding effects are small, where you're looking at a population that doesn't have a big spread in metallicity, et cetera. It is, I think, an extremely promising method. It's been applied now to hundreds of galaxies. It can be applied much more easily than the Cepheid distance scale can, simply because you don't have to worry about variability. And so I think we'll get into future, but as we move now into the JWST era, it's got a lot of promise. And we've talked about the I-band luminosity function. And we can talk in a few minutes about the moving into the infrared, but it's a distance indicator that's been with us for a century. It's not as well known as the Cepheids, but it has a large number of advantages. And I think if we're going to address the Hubble tension, ultimately we need to have many methods with high precision and accuracy, and the tip of the red giant branch is going to be one of those methods.
Very cool. Thank you very much, Wendy.
I also want to give a shout out to our collaborators on this. We have a graduate student, Kayla Owens at the University of Chicago, and postdoc In-Sung Jang, who are also collaborators in this effort.
Very nice. Good shout out. Good shout out. That was really awesome. That was nice. Thank you so much for walking us through your very lovely article.
One thing that should be pointed out is that there is a lot of interest in using this method on JWST.
Okay.
Many people are exploring the application to longer wavelengths. I mean, JWST is not designed to be a BVRI. It only has sensitivity in the blue.
In the red.
Around, towards the blue, near to the I-band. But it's inefficient, and the higher efficiency of JWST is in longer wavelengths. But the caveat is that if you change wavelengths for the tip of the red giant branch, you lose the zero sensitivity of the tip to metallicity. Okay.
Only that. Okay.
Well,
so we're talking about moving into the future now and how we will address this.
Right. So is there, you mentioned, JWST, maybe 100 galaxies. Do some of these other forthcoming telescopes maybe get us up another factor of 10 in that? Is there, so there are additional observations, additional theoretical models. So where do we go with this over the next couple of years?
Yeah, I think what's really clear is that we're going to be able to extend it to many, many galaxies. So not only for the Hubble constant, but also for measurement of local flows and understanding our local neighborhood with hundreds of galaxies is a method that could be applied. So we've got Roman coming up, which is going to be a great survey telescope. We've got JWST. We're exploring and trying to understand what is the best combination of filters with which to apply the method. And we've given you the advantages of the I-band, which is that the luminosity of these stars is constant with color. As Barry's mentioning, you have a slope in the infrared, so we need to understand how to calibrate that slope, and we're putting a lot of effort into now trying to understand how to do that and what best combination of filters will let us do that well in terms of both efficiency and then, of course, accuracy. So I think JWST is going to, for the next few years, tell us much about the distance scale. So not only tip of the red giant branch, but also Cepheids, and another method that Barry and I have been developing along with students and postdocs at the University of Chicago using carbon stars. So I think it's pretty exciting time in the distance scale now. And I think in just the same way as we saw a huge jump with the availability of Hubble at the time of the launch of the Hubble Space Telescope, we were in, trying to understand why the tip of the red giant branch and photographic plates and Cepheids and there were differences became really clear once you got much better data, higher resolution, less sensitivity to reddening and so on. And then we stopped arguing about the factor of 2 that had played the distance scale for so long. I think we're at the few percent uncertainty level now, and people will argue, is it 2 or 5%? Some people will even argue that it's 1%. But I think JWST, with its higher resolution, higher sensitivity, is going to take us again into a whole new regime. And we're seeing that now, where the resolution in the HST images, understandably, is just not as high. Sensitivity is not as high. And boy, do you learn a lot when you get a higher resolution, but what's been crowding you, particularly in the Cepheid distance scale. So I think that's what's really exciting us right now, is this new machine that has much, much greater capability, and we're going to learn a lot.
Cool.
But I think that we're going to be in for a little bit of turbulence in this flight, so we should fasten our seatbelts, because moving into new wavelengths for the tip of the red giant branch, and there's going to be a host of people applying it and trying to figure out what the best combinations of colors and filters are. And there are going to be some naysayers saying that it doesn't work and it's falling apart. And we're just going to have to keep our cool and get high precision data and work through these issues, because the stars that define the tip in the I band are precisely the same stars that define the tip at all the other wavelengths. Okay, so it's just a matter of understanding how their colors and luminosities translate and map to the other filters. And there are wonderful programs by Kristen McGuinn
Shout out.
are attempting to do this, and we will see the results, and those will be made public, and lots of people will be
Happy.
benefiting from that.
Happy.
Some will be unhappy, but that always happens. Very cool. Very nice. Well, I really look forward to seeing this method advance over the next couple of years with these new telescopes coming online and uncertainty studies like the one you've done here. It's very nice. Very cool. So Wendy, Barry, thank you so much again for walking us through your very lovely article.
Well, thanks for the opportunity.
Yeah, thanks for your interest.
Sure, and that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.